Good morning to lesson 11, the standard model. Okay, so we're now going on to what's called the standard model, which is basically the model of how the universe is at the moment as we feel. Now, back in, if we go back to class 1, okay, back in the mid-1930s, everyone was very happy, okay, because everything had been discovered. They had, the Bohr model was there, which explained things very well, and on top of the Bohr model, Chadwick, as you saw in one of the films, had discovered the neutron in the early 1930s. So we had the model that you kept drawing last year, time and time again during chemistry, okay, and all was good. The problem was, what followed then was that new particles started being found, and suddenly this beautiful existence where we only had three fundamental particles, the proton, the neutron, the electron, was thrown into doubt, okay, and this happened in two ways. Number one, they started investigating these cosmic rays. These cosmic rays are rays, this is the Earth, okay, so the cosmic rays, right, okay, are rays that come from outer space, okay, and they started investigating these cosmic rays and how they interact with matter, and they started finding these particles that seemed to be different, and they started naming these particles. They weren't sure what they were, and that was okay for a while. Then they moved on to particle accelerators after Cockcroft and Walton's experiment, and they started hammering particles together. Okay, and when they hammered particles together, rather bizarre things happened. Now, this is what's happened at the moment in the Large Hadron Collider. So at the moment, you have these big circular accelerators. Okay, and what you do is you get two protons or something like that, and you send them in opposite directions, and you get them really high speed. You get them to hammer together. Okay, you get them to hammer together, and what happens is quite remarkable. Okay, now regarding the particle accelerator, let's get clear. The particles have to move in a circle. Now, to get anything to move in a circle, you must apply a force. It's called a centripetal force. We'll come back to it later when we're doing mechanics again. Okay, magnetic fields provide that force. That's magnetic fields provide the centripetal force to keep it going in a circle, and electric fields, in the same way as they did for cathode ray tubes and for X-ray tubes and for Cockcroft and Walton's experiment, are provided by electric fields. So electric fields keep accelerating the protons around and around and around and around. The magnetic fields keep them going in circles, and then you hammer them together. Now, what happens when you hammer them together is quite remarkable. Okay, it'll make sense to you because it's the reverse of what we've been looking at before, but it is quite remarkable. So let's take an analogy. Okay, right. So what we have is we have a proton, and we have another proton. We have two protons. These are not atoms, these are protons, okay? And what happens is, okay, that you get these protons traveling at huge speeds, very close to the speed of light, unbelievable speeds, and you hammer them in together, okay? And what happens next is really important, and this is something that people miss out on a lot, okay? So you hammer the two, no, we're going to do this in slow motion, okay? You hammer the protons together. Boom, okay, they hammer together, okay? And that's fine, right? And afterwards you detect what's there. And what you detect, and this is the bit that people miss, is you detect one proton. You detect two protons. Both of the protons are still there. Both of the protons are still there. They have lost kinetic energy. What has happened to kinetic energy? Quite remarkably, what has happened to the kinetic energy is that we have got new particles. We have a grape particle, raspberry particle, another grape particle, and to beat it all, we have a cherry particle. Now, this is the bizarre thing. Okay, so watch. You had two protons before, with a very high kinetic energy. Just dropped one of the protons, okay? You now have two protons after with less kinetic energy. The kinetic energy has changed into mass, into matter, okay? And the kinetic energy, the matter, has made these new particles. These are the new particles. So this was before, okay, and this is after. Okay, so it's an amazing experiment and a very tasty one. Okay, so that's what's going on. That's what's happening in the in a particle accelerator. So if we write one of them, for example, this can happen. Hydrogen, proton plus proton. Now this is the funny bit. Still proton plus three new particles or two new particles, whatever. So there is these particles called pions. Okay, and sometimes you get three pions. Now, The charge of the 3 pions, their mass will be very small, negligible, so the mass numbers will stay the same. Okay, and the charge of the 3 pions has to add up to 0 because the charge before is +2, the charge after has to be +2. So you could have what's called a positive pion, a neutral pion, and a negative pion, or whatever. The charge of the 3 particles afterwards has to add up to 0. Okay, and the mass of the 3 particles has to be equivalent to the energy loss as such, okay, using E is equal to mc squared. So let's go back to the E is equal to mc squared. Okay, the mass, that's E is equal to mc squared. We've done a lot of calculations now. We're going to do one new one tomorrow in your next one. Okay, where we're converting mass to energy. Here we're doing the opposite. We're converting energy to mass. So if I rearrange that, the mass is the energy over c squared. Okay, so the kinetic energy of the particles that's lost divided by c squared gives us the mass of the particles. You need a huge energy to get even a small mass. That's that. So when we're doing all these experiments, they were discovering more and more and more and more new particles, and the whole thing went mad. Okay, it went mad, and it became known as a particle zoo. Okay, particle zoo. Physicists don't like this. They like things to be more straightforward. So they came up with a theory that perhaps protons and neutrons aren't the smallest thing. Maybe there's something smaller. Okay, and this is where the quark model, okay, what's called the quark model, came about. Okay, and it has been proven since to be correct. Okay, so let's have a look now. And what we're going to do now is we're going to look at what's called the standard model. Okay, so the standard model. Right. Now, the standard model is it. This is what we think at the moment, right? And we have 6 what are called leptons. We have 6 quarks, as we'll see, and we have 4 forces. Now, we've already looked at the forces, so let's just write these down and we'll come back to them in a minute. We have the strong nuclear. We haven't dealt with the weak nuclear, but we will know in a minute. I'm going to put a dotted line here with the electromagnetic and with the gravitational. They're the 4 forces. Okay. Now, over here, okay, we have leptons. Now, leptons are fundamental particles, or elementary particles, particles that cannot be made any smaller, okay, and they are called the electron, okay, the muon, and the tau, okay, 3 particles. They are increasing in mass, okay, and they all have a charge of -1. They all have a charge of -1. That's a bit of a problem here, I manage, okay. As well as these, we have the neutral version, and these are called, and you heard this before, these are called the neutrinos. Now, these are a little bit unusual, to put it mildly. But suffice to say at the moment that they're neutral. Okay. In this course, we're really only interested in the electron and the electron neutrino. Okay. And we have what's called an antineutrino. We'll come back to that in a minute. Right? We have 6 quarks. 6 quarks. So the 6 quarks these are what protons and neutrons are made up of. Okay, and the names aren't the most imaginative. Okay, but let's have a look. We have up, down, charm, strange. The strange one was called a strange quark because it was unusual at the time. Okay, it wasn't doing what they expected it to, so they called it strange quark. Okay, and we've top and bottom. Now, when this came out in the 1970s, some American universities were not happy that a fundamental or an elementary particle would be called a bottom, which is a bit rude. So sometimes these are called truth and beauty, but we're sticking with top and bottom. We'll get over it. Okay, symbols for these are U, D, C, S, T, B. Okay, we'll go through this on your notes in a minute, so you don't need to be, just watch as we go. Okay, now the charges of these are very strange. +2/3 for the top ones and -1/3. They are fractional charge. Now remember, the charge is a fraction of the charge on the electron. The charge of the electron is the fundamental unit of charge. Okay, and you can't have anything that exists that isn't a whole number times the charge on the electron, either 0, 1, 2, 3. So you actually can't have a quark on its own, because there's a charge 2/3. They have to exist in groups or in families, as we'll see. It's all about the family, right? Now, that's it. That's what everything in the universe is made up of, and that's how everything in the universe interacts. we go to the forces. Remember, the strong force, we know it holds the nucleus together, and it also holds the proton and the neutron together. So it's the force that holds these quarks together to form the little families, as we'll see in a minute. Okay, the weak force is the force associated with beta decay. It's the force associated with beta decay, which is the decay which, remember, a neutron decay into a proton plus an electron plus an antineutrino. It's beta decay, and it's the weak nuclear force. Okay, and the electromagnetic and gravitational forces. Okay, remember, the electromagnetic force is the force between charges, and the gravitational force is the force between masses. And every force we experience in our everyday life is either an electromagnetic or gravitational force, usually a gravitational force. Usually an electromagnetic force, and sometimes a gravitational force. There are 4 forces. There are also what are called force carriers, these things that basically cause the forces to interact. We don't actually do it in the course, but it's worth knowing of their existence, okay? And the force carrier for a strong nuclear force is quite appropriately called a gluon. So a gluon is this force carrier that passes the force, causes the force to interact, okay? These are called W and Z bosons. They're called bosons, okay, W, Z bosons, okay? The electromagnetic is the photon, okay, so think about it, electromagnetic waves, okay, electromagnetic forces and electromagnetic waves can be considered to be photons, and what carries the force for electromagnetic waves is called the photon. Don't worry about those, they're not relevant to us. And this one, gravitational force, well, you'll see optional videos later that involve talk about Higgs boson and so on, okay, the Higgs particle and so on. So have a look at that if you're interested. It's not on the course, okay, so these, sorry, I didn't even write them down. The bosons, okay, are not on the course, but it's just interesting to be aware of, okay. What is on the course is all of these. Remember, very important about these only apply within the nucleus in a very small area, okay. These apply everywhere, and they're infinite as such. If you 2 plus charges together, and if you move them 10 meters apart, well, there's still a tiny force between them. If you move one of them to London and one to New York, technically there's still a force between them. It's negligible, but it's still there, okay? These both obey what we call the inverse square law when we're doing gravitation later, and when we're doing Coulomb's law later in electrostatics. We'll be dealing with those again, so we'll come back to those. But just remember, they're infinite forces, technically, okay? Right? These are the forces. The most important thing to be aware of regarding the forces, and we'll see it in a minute, is that the weak nuclear force, okay, leptons, this is the most important thing. Leptons do not experience the strong nuclear force. They're not affected by the strong nuclear force. You could think in terms of that. When the electron is emitted in the nucleus, it's not held in by the strong nuclear force. So it can get out of there, okay? So think about that one, right? These are our forces. That's it, okay, that's it. Now, the only other thing we have to look at regarding the Standard Model is how these are put together, how the quarks are put together. They can't exist on their own, they exist either in 2s or 3s, okay? Before that, let's get clear, every particle has an antiparticle. We've spoken about this already. Every particle is an antiparticle. We've spoken about in pair production and pair annihilation. So the anti-electron is called a positron. The anti-muon is called the anti-muon. The anti-tau is called the anti-tau. Even neutral particles have an antiparticle, even though they're the same charge, because there are other properties called spin and so on, which we don't go into, which do change. Okay. Same with these, anti-up, anti-charm, anti-so on, all antiparticles, and an anti-up particle has a charge of minus 2/3 rather than plus 2/3. Okay, right. But the important thing again to reiterate, leptons don't experience a strong force. We'll see all this in our notes in a minute. Okay, right. So I'll look at now is the idea of the quarks. How we make up the quarks. Okay, so families of quarks are called hadrons. Okay, they're called hadrons. Families of quarks, and we have 2 types of quark. We have the baryon. No, hadron is in Large Hadron Collider. We have the baryon, okay, and we have the meson. The baryon has 1, 2, 3. Okay, the baryon has 3 quarks or 3 antiquarks. The meson has a quark and an antiquark together. But the math is interesting. Remember, you can't get when you put them together, their charge has to add up to 1. So we're only going to worry about the up and down quarks because they're the ones that exist in nature. Okay, these are the ones that exist. We're all made of up and down quarks. Okay, the other quarks only exist for very, very short periods of time. So the up and down quarks are what we're interested in regarding examples. So let's take a proton. All right, it has to add up to +1. Now I could leave this as an exercise for you, so you can pause it there now and you can figure it out. Okay, you're back to me. Okay, and a proton has to be an up, and a down. Okay, think about it. 2/3 plus 2/3 is 4/3, minus 1/3 is 3/3, plus 1. So that's what a proton. Up, up, down. A neutron, up, down, down. Okay, up, down, down. 1 up, 2 downs. Okay, 2/3 minus 1/3 minus 1/3, 0. What about an empty proton? Well, let's have a look. It would just be empty up, empty down, minus 2/3. No, sorry, instead of 2/3 is minus 2/3, minus 2/3 instead of minus 1/3 plus 1/3. So it has a charge of -1. Quarks, let's just look. Up and empty down. So a quark and an empty quark. So that's 2/3 plus 1/3. So that would be 1. Okay, that's a pion, positive pion. And let's take empty up, down. Would be minus 2/3. Minus 1/3. Okay, it will be -1, and so on. Okay. Now remember, quarks feel all the forces, so hadrons feel all the forces. Baryons and mesons are the families of hadrons. Okay. Now mesons or mesons have other uses as well, as we may see at times, but it won't be too relevant to us in the course. Okay, so there's a lot in that. Worth looking over again and follow through now and watch as we update the notes, we'll add further information this time instead of just filling in things, so it's important to watch that as well. Thanks a million.